Okay, so a couple of things. There was some confusion, I think, regarding a couple examples we did in class that kind of have come out here when some of you guys are working on your WebAssign homework for section 4.3. So I thought I would do a video on this question number 8, and then I'll do one on question number 9, and so that I think that'll clear up the confusion. So anyway, when we're finding critical numbers, so here's a function x squared over x squared minus 5. When we're finding the critical numbers here, these critical numbers have to be within the domain of the original function. So as you can see on this one here, there's a domain restriction here where x cannot be equal to 5 or negative 5. And so, for example, when we're finding critical numbers then, which is the first part to the problem, to find critical numbers, and we go down here and we take our derivative of f prime, and so here's the derivative, and you can see, okay, we want to find out when is the derivative equal to 0, and certainly that happens at 0 because that would make that denominator equal to 0. So that is one of the places. And then we also say, well, where does the function, where does the derivative not exist? And so that would be at 5 and negative 5, because that would make our denominator 0. However, the problem is that these are critical points. I know they're called critical numbers here, but they're actually supposed to be points on the original function that these relate to. And so since 5 and negative 5 are they're not in the domain of the original function, they cannot be points that are called critical because they're not actually points on the graph. So an adjustment to, I guess, my lecture would be is we need to make sure that, and I think I said this, but I think in the first example I skipped over it and didn't actually follow that rule. And that's my fault. I kind of rushed through that problem. So what we need to realize is that any critical numbers have to be within the domain of the original function. And in this case, 5 and negative 5 are not. So on WebAssign, it's only going to count as critical numbers x equals 0. If you try to put in 5 and negative 5, it's going to count it wrong because they're not within the domain of the original function. Now notice here on the answer key for WebAssign, it's telling me, and I know you don't see this, but there are discontinuities at negative 5 and 5. And that's where the function doesn't exist. And actually, when you look at the graph, we'll look at that here in a second, those are going to be locations of vertical asymptotes. And we need to actually have those discontinuities on our sign chart, and I've got that down here when we go to find the increasing and decreasing intervals, that we need to not only put critical numbers on the number line here for our sign chart, but we do actually need to have the locations where there are discontinuities, and because that could be a place where the sign of the derivative changes. So even though those aren't critical numbers, we still need to put those discontinuities on the sign chart because they can be places where the derivative changes sign. Okay, so that's why you see on here, as I put down my sign chart, I have not only 0, the critical number, but also these places where the function's undefined. And when you plug in numbers in each of these intervals, you'll find out that the sign of the first derivative is positive here between negative infinity and negative 5. And then it's positive also between negative 5 and 0. Now, I know it didn't change sign there, but it is possible to have a function where at that discontinuity of negative 5, it could be a place where the sign changes. And then at 0, between 0 and 5, the first derivative is negative, and then from 5 to infinity, it's still negative. So we have positive, positive, negative, negative, And so down here, this is how we would report our intervals on which the function is increasing or decreasing. And so we only have one place where there's a change in sign here of the first derivative, and that's at 0. So when it changes from positive to negative, so that means it's switching from increasing to decreasing. So when you have something that's changing from increasing to decreasing, increasing here and then decreasing, so you're going to have there a relative maximum. So there's a relative max here at 0, and we have to give the coordinate for that. So you have to plug in 0 back into the original function up here. So if I put in 0 in the numerator up here, of course the entire function is going to be 0. So the relative maximum coordinate is 0, 0. Now, last thing is they asked to take a look at the graph to confirm your results, and I know we didn't really do that in class that much, so I wanted to actually kind of show you the graph here. That I put it in Desmos, and I superimposed down here on the bottom our sign chart so you can kind of see what's going on. As we trace the graph from left to right, look what happens here. As I start off here from negative infinity and I go towards 5, of course 5 is here, excuse me, negative 5 is there, and then 5 is over here. So as I go from negative infinity to 5, what's happening with the function? Well, it's increasing, and so that's why I have a plus sign here. That would mean the first derivative is positive if the function is increasing on the interval. And so then, of course, we have a vertical asymptote here at negative 5, so nothing's there. But then as we pick up there and keep tracing, look, we're moving up, so that means the function is increasing here until we get to 0, and that's when it switches over to decreasing. And so that's why it's positive here from negative 5 to 0, and then negative, the first derivative is negative from 0 to 5. I didn't put that down there, but that should be a 5 here. And then as we jump across this vertical asymptote here at 5, then we are going to decreasing, and so therefore the first derivative would be negative. So hopefully that clarifies that and also corrects a mistake that I made in class. So